from Brown University. And he's going to talk about quantitative derivation and scattering of the 3D cubic NLS in the energy space.
Yes, thank you to Honja and Connor for the invitation to speak today. This will be a discussion of joint work with Xuwen Chen at the University of Rochester. I just got to notice this meeting is being recorded. I should click continue to allow for that, right? Okay. All right, so let me give some discussion of the setting. The context here in quantum mechanics, multi-particle systems are modeled by an n-body wave function. So that is psi n, which is a function of time and space, coordinates x1 through xn, where each xi belongs to R3. And let us assume that there is a normalization in place so that the L2 norm of this function is fixed at 1. And it is, in the course of the talk, convenient to use a boldface vector notation in which boldface x sub n denotes the n-tuple x1 through xn, and so itself is an element of R3n. All right, the physical interpretation of an n-body wave function is that the mapping taking, say, x1 into the density squared integrated out in the remaining particles, x2 through xn, is the probability density function for the first particle and analogously for the other particles in the system. Now, systems of identical particles must have the property of symmetric probability densities. If the two particles are truly indistinguishable, then we should be able to switch their places, and then the densities should be the same under that interchange process. So therefore, if we have that the complex modulus squared agrees for two particles, psi of x1, x2 versus psi of x2, x1, if the complex modulus agrees, then there is some phase theta such that psi of x2, x1 is equal to e to the I theta psi of x1, x2 under this particle interchange process. And so if you do this interchange twice, then you should get a multiple of e to the 2I theta. But that brings us back to where we were. So therefore, we can only have that theta is equal to pi or theta is equal to 2 pi, giving us either an antisymmetric wave function, which is called a fermion, or a symmetric wave function, which is called a boson. And this extends to n-particle systems. The wave functions for identical particles are either antisymmetric, in which they are fermions, and symmetric, in which they are called bosons. So today we study boson systems. And so then that means a boson system of m particles just means that psi n of t, x sigma 1 through x sigma n is equal for every permutation sigma of 1 through n. And so whether the particle is the fundamental particle is a fermion or a boson is some intrinsic property and characterized by the quantum spin, which can be either 1/2 for negative, is either half integer for fermions or integer valued for bosons. And so an example of a famous example of a fundamental particle that is a boson is the Higgs boson, which was predicted in 1964 by Higgs and first observed at the Large Hadron Collider in 2012. Then when you combine elementary particles into composite particles, the spins add. And so as a result, you can get composite particles, which are either fermions or bosons, depending upon the spin of its constituent parts. And so some atoms that are bosons are lithium-7, rubidium-87, and sodium-23. These are bosons and have in fact been made into Bose-Einstein condensates, which we discussed in the lab. The dynamics of an n-body wave function are governed by an n-body Hamiltonian. So we will use as a Hamiltonian Hn, which consists of Laplacian terms and an external potential and interaction potential components, where the external potential is a confining potential. And we have scaled the pair interaction potential terms so that they are of the form V sub n of xi minus xj, so that is the I and j particle interaction. But the scaling Vn is given by n to the 3 beta V n to the beta x for some beta between 0 and 1. And the V is assumed to be symmetric. So actually this double sum could be replaced by a sum over I less than j. And the pair interaction potential is a smooth and spatially decaying. So as we proceed in the equations throughout the talk, I will often use the boldface notation again, but whenever Laplacian sub boldface xn, I mean the sum from j equals 1 to n of Laplacian xj over the individual particles. So this whole term just denoted by a single Laplacian. So in the work I present today, we drop the external potential, but physically it is natural to have some type of harmonic confinement. So there's results both with and without external potentials. The pair interaction potential can be either positive or a negative function in experiments, and the effect on the structure of the condensates that we discuss is through the scattering length, which can be itself positive or negative. A first order approximation to the scattering length of the potential Vn with the Gross-Batievsky type scaling that we're considering is such that 8 pi times the scattering length is equal to the integral of V. So you can think of examples of V giving positive or negative values for the scattering length. Right, so that is an approximation as long as beta is less than 1. So then we can consider either the stationary eigenvalue problem, which is of the form h psi is equal to E psi, especially consider the ground state properties, or we could consider the time-dependent evolution given by the n-body Schrodinger equation. So that is I dt psi is equal to h psi. And for the time-dependent problem, if we start with initial data satisfying the symmetric condition that the wave function is symmetric and represents a boson, then the solution will satisfy that property for all time, since the Hamiltonian itself is invariant under permutation. Now, in the stationary case, the system is said to exhibit Bose-Einstein condensation if approximately this ground state eigenfunction factorizes in the sense that it is approximately equal to a product of one-body wave functions, phi, evaluated identical one-body wave functions, phi, evaluated at x1 through xn. And the mathematical meaning of this approximation requires some clarification, of course, and that's the substance of the talk, but because what we mean is that this approximation becomes valid as n tends to infinity, but as n tends to infinity, we're talking about functions on different spaces. Right? This is a function in L2, 3n, and then n is taken larger, so we have to be precise about the meaning of that. But this statement is interpreted as physically as all particles belong to the same state. So this is a situation which is possible for bosons, and fermions, on the other hand, obey the Pauli exclusion principle. Now, as the ground state of a quantum system, Bose-Einstein condensation is only achievable at very low temperatures. It was first predicted by Bose and Einstein nearly 100 years ago in 1925, but it only achieved in the laboratory with the rubidium-87 gas at Gila, University of Colorado, by Cornell and Wieman in 1995, and 4 months later by Katerla and his MIT group with a sodium-23 gas. And they all shared the Nobel Prize in 2001 for this achievement, but required combination of many experimental physics techniques called optical cooling, magnetic trapping, evaporative cooling, all necessary to bring the gas down to the nanokelvin temperature range. And these gases are very dilute, low density, like 1/1,000,000th more dense than atmospheric pressure. And the number of atoms in the condensates are on the order of thousands. So N is like a few thousand. Now, it's also of interest to see how a Bose-Einstein condensate will evolve. So that is, we take the time-dependent Schrodinger equation with an initial condition, which is of this factorized form. But that this factorized form is not necessarily corresponding to the ground state of the operator Hn. Indeed, if it just corresponds to the ground state, then the time evolution is trivial. So the situation in which it's factorized, but not necessarily the ground state of the operator Hn, arises, for example, if a ground state condensate is prepared with one external potential and one interaction potential, and then these are abruptly experimentally adjusted to some other external potential and interaction potential respectively. So you end up abruptly changing the operator, and then you're given an initial condition from a ground state of a different operator. So then the dynamics are expected to be interesting. And it is actually possible to adjust the interaction potential by a method called Feshbach resonance management. So the scattering length can be tuned. The expectation is that when we consider this evolution problem, that psi n t x n will be approximately a product of one particle wave functions phi depending upon time, together with a phase correction, and the one particle wave functions will solve the nonlinear Schrodinger equation. So that's I dt phi is equal to minus Laplacian phi plus b phi squared phi. So this nonlinear effect is a remnant of the interparticle interaction in this scaled limit. So there's a few ways to study this problem mathematically. And so the one that we adopt will pass to the densities, the corresponding densities. So the n-body wave function, psi, is then placed into a density, gamma sub n, evaluated at xn and xn prime. We just set equal to psi at xn times psi of xn prime bar. And this is the kernel of the orthogonal projection onto the one-dimensional subspace of L2, spanned by the n-body wave function psi n. Recall that it's been normalized. So that's why it's a density, because it's a kernel of a projection operator. And then we also need to look at the marginal densities. The marginal densities are just obtained by taking the n density and taking the trace over the last n minus k particles. So for a fixed k, we trace over the last n minus k particles. More explicitly, we take boldface xn, the n tuple of components from x1 to xn, break it into the piece where for the first k, which is just a boldface xk, and the last n minus k are grouped into x boldface x minus k. And then we're looking at a kernel, which function of xk and xk prime, which is obtained by taking the gamma n density and evaluating the setting the x n minus k equal to x n minus k prime, and integrating over that 3 n minus k dimensional space. So that is the trace. So, although before you start taking traces, when k is equal to n, that is an orthogonal projection onto a one-dimensional space, a rank 1 operator. For other k, these operators, these marginal operators, are just more general trace class operators. So using that So then to proceed with the analysis, we need the equation that is solved by the K particle marginals, gamma n upper K. So starting with the fact that psi n solves the n-body Schrodinger equation and using the symmetry of that psi sub n, we find that gamma nk solves this equation, where the Laplacian terms have just come down from the Laplacian component of h sub n, but only for the first k components, and the remaining n minus k have disappeared into the trace. As far as the interaction, the external potential has been set to 0, but for the interaction potential terms, the terms for which both coordinates xi and xj are less than or equal to k survive and show up here in this term. And so there are on the order of k squared such terms, and there's the 1 over n coming from the operator. But then there's also the case where both xi and xj are greater than k, but those disappear in the trace. And then finally, there are the cases in which I is less than k, but j is greater than k, in which case you can appeal to the symmetry of psi n and then equate all those to the case in which j is equal to k plus 1. And so we're left with the Vn xi minus xk plus 1 and xi prime minus xk plus 1 prime. But the xk plus 1 coordinate is still being traced out. So there is xk plus 1 prime are set equal, and then equal in the potential terms, and then integrated. There's a dxk plus 1 on the right here of the slide. And so there are, the count of such terms is n minus k times k, and well, the k is represented by the sum, but then otherwise there n minus k terms have been bundled together with the symmetry assumption and all set equal to k plus 1. So if we're thinking the analysis in k is small, in fact, we'll always be using k less than or equal to log n, so much smaller than n, then this coefficient is O of 1, but the 1 over n here is small. So this is potential term, which just references the gamma nk, has a small coefficient at least, and the this term, which actually references the next density, next higher density in the hierarchy, the k plus 1. We call this the interaction type term and has an O of 1 coefficient. So in operator notation, right, so if you view the gamma n upper k's as operators, then this equation takes a more concise form. Because, for example, this expression is a commutator of gamma n with the Laplacian. And likewise, these become commutator terms, and then you can use trace notation. But we actually prefer the first one because we want to estimate, and so we want to look at it as a function of x and x prime. But if we're going to look at it as a function of x and x prime, then we need some more compact notation. So the kth internal potential we denote as Vn upper k, and that's a function of xk and xk prime. So that is this sum, which back here then just multiplied gamma n upper k on the right-hand side. And this term we can simplify by saying that it is the result of a collapsing operator applied to gamma n upper k plus 1. So we define the collapsing operators. And that will be where you take Vn xi minus xk plus 1, multiply by the k plus 1 density, xk plus 1 prime is set equal to xk plus 1, and then we integrate in xk plus 1. And then there's an analogous one for the second half, in which there's a prime here, and a prime here. And then the The term that shows up in the interaction part involves the difference between these collapsing operators, and then we also sum from 1 to k. So with that, with all those abbreviations, then the equation for the kth particle marginal is IDT gamma k. Then there's Laplacian stuff, a potential type term with a 1/n coefficient, and this bundled potential has potential type terms that are being scaled towards deltas. And then there is this interaction type operator involving a trace over the last just xk plus 1 component. All right, so you can then better visually examine the different components of this equation. All right, so the equation for gamma n k we see it's linear, but it is a couple. So on the right hand side there is gamma n k plus 1 in the equation for gamma k. So if you write the equation for gamma 1, then it has gamma 2 on the right side, and then the equation for gamma 2 has gamma 3 on the right side. And the system does not close until you reach k equals n, and then n is the thing that is being sent to infinity. So this full coupled system for all k's is called the BBGKY hierarchy after these physicists. So it's coupled, but it is linear. But in this form, we can assess what we expect as the limit. So in this form, so I've repeated the equation. Let us evaluate the formal n to infinity limit. So recall, first of all, let's look at the potential term. All right, so that was a sum over Vn xi minus xj and xi prime minus xj prime. And the Vn's individually are of the form n to the 3 beta v n to the beta x. So they have a weak limit, which is a delta function. And so then collectively, this converges in some weak sense as n tends to infinity to these deltas. But the term is prefaced by a 1/n. So we can say, all at the formal level here, that the 1/m will bring us to 0. This will be brought to delta, so we'll just have 0. And the expected contribution of the potential part term should be 0. However, this term must be actually properly accounted for, because convergence to delta is actually some type of singular convergence, and so it all depends upon how things are estimated, whether the strength of that singular type of limit is comparable to n or not. And so the proper analysis uses wave operators, and then you actually find that when beta is equal to 1, this term does have a non-trivial effect and affects the nonlinear coupling coefficient that results from here. But when you take beta less than 1, it is indeed true in some sense that the potential part term has no effect in the limit. So the components of the collapsing operator, on the other hand, so there's one more term for which we need to assess the formal limit. So the components of the collapsing operator look like this. So we had Vn evaluated xi minus xk plus 1, multiplying the k plus 1 density, and then matching up and integrating in the k plus 1 coordinate. All right, so that's the Bn plus operator, and there's also the Bn minus operator. So each of these, again, if you just take the Vn, replace it in the limit as n tends to infinity with the delta, then you get this, and this is something where you can you have an integral and there's a delta, so it allows us to just replace xk plus 1 here and here with xi. So that's what I've done, and so now we have the k plus 1 marginal evaluated at xk, comma little x, plain xi, xk prime bold at comma xi. So there is a pairing of 3 different terms. There's 3 xi's in this whole list. And so we just take this type of operator, which does that pairing of 3 different terms, and call that the Gross-Pittievsky collapsing operators. So they are given by these formulas. And then you can bundle them together into a difference and sum from 1 to k. And then you have what we expect to be the limit. So if we were to assume in some reasonable sense that gamma n k converges to something that we call gamma infinity k, that thing gamma infinity k should solve the equation where the potential part term has disappeared, but the Laplacians have carried over, and then the interaction stuff has now given us this new Gross-Pittievsky type interaction. And so that equation is also a coupled hierarchy. We see here that the evolution of the kth component is driven by the k plus first component, but that is called the Gross-Pittievsky hierarchy. It is also linear, but now it is in fact infinite. So instead of going from 1 to n, as was the case for BBGKY, this extends all the way to infinity. This hierarchy, however, does have a special solution. And that suggests that there might be something to learn from this approach, that if we just set gamma k to be equal to a k-fold product of nonlinear Schrodinger solutions, and then the complex conjugates with the prime coordinates on the as well, then you can check directly that if phi satisfies the nonlinear Schrodinger equation, then you plug this gamma k into here, the Gross-Pittievsky hierarchy, and you find that it works. It solves that equation. And that's just because this nonlinear term is capturing the effect of these Gross-Pittievsky collapsing operators that we defined here, where certain components are being paired together. Now, this is the nonlinear Schrodinger equation, and when b is greater than 0, we call that the defocusing case, and when b is less than 0, the focusing case. So here is our theorem. We'll start with the assumptions. So suppose that the pair interaction potential, V, is greater than or equal to 0. And so then the first order approximation to the scattering length of V sub n that we denoted B, given by the integral of V, is positive. And then at the NLS level, we're dealing with the 3D defocusing cubic NLS, and that's in R3. Secondly, suppose that we take phi 0, one particle function, just a function on R3, as initial condition for this Schrodinger evolution. Just say that the H1 norm squared is bounded by some constant E0, and take phi of t to be the H1 solution to this 3D cubic NLS. So then with that ingredient, then just define gamma upper k to be the corresponding solution to GP. So we have a very specific reference solution to GP. Then suppose that n-body energy bounds hold. So that is that the n-body wave function solving the n-body Schrodinger equation is assumed to satisfy bounds of this type. So you take the Hamiltonian, the n-body Hamiltonian, normalize it by multiplying by n to the minus 1, apply the power k, and then pair that with psi n. And at least, when k is equal to 1, you see how you get one type of energy. When k is larger, the dominant terms in this expression will involve Laplacians landing on different components. And actually from that, you can extract a positive lower bound as shown in earlier papers by Erde, Schlein, and Yau. But we are just going to assume, as part of the assumptions to the result, that this kth order energy is bounded by E0 to the k. And then it suffices to assume that, though, when t is equal to 0, because the time evolution of this is it's constant. It's constant in time by energy conservation. It's n-body Schrodinger dynamics. All right. So then we have an n-body linear Schrodinger solution, and we're also making reference in our assumptions to initial condition for NLS, corresponding evolution phi for NLS, and corresponding solution gamma k to GP. And so we need some assumption that relates the two at time 0. So we suppose that the n-body initial data satisfies the following, that for every k, that if you look at the kth density gamma nk, the component of BBGKY, built from the n-body wave function, minus gamma k at 0, the density built from the phi zeros, which were then evolved by NLS. You look at this difference and then evaluate in H1, and we want that as n tends to infinity to go to 0. Right? So that is just saying that initially the two match up asymptotically. And then the conclusion is going to be one in which the corresponding solutions match up asymptotically. So then uniformly on time, and time is up to E0 to the -2, so it is a short time result. We have that the H1 norm of the difference between the n particle kth density and the kth GP density associated to NLS, bounded by a certain expression giving us the rate at which this is going to go to 0, right? And that is dominated for small beta, right? So this is valid up to beta equals 2/5, but for small beta, beta less than 2/7, it is dominated by this term, which is very close to being 1 over n to the beta. And 1 over n to the beta, we can show is understood to be the optimal rate at which we could expect a result like this. All right, so we attain the optimal rate, but just with a slight log loss. Although I'll say that the main feature of this is that everything is done at the level of H1, which is the energy space. And so other approaches involve a regularity difference, and that's what we were trying to avoid. Yeah, so these terms come from different sources, and so there is a limit in how far we can push beta at this point, but there is hopes for improvements and possibly the complete elimination of that term, which is what we would like to see. So before I give the main features of the result and the historical overview, comparison to existing literature, let me just state a main step in the analysis, because I'll refer to that when I talk about the literature. So as we have said, we let phi of t be the H1 solution to the 3D cubic NLS. And then we build from that a solution to the Gross-Podolsky hierarchy, as stated here. Well, we could do the same thing with the Hartree nonlinear Schrodinger equation. So that is, we could take the same initial condition phi sub 0 and let phi sub h denote the solution to this nonlinear equation, where instead of the pure power, phi squared, we take phi squared and convolve it with Vn, which is close to, it's approximately the delta. So in the n to infinity limit, we see that it does become just phi squared. But for finite n, it's Vn convolved with phi squared times phi h. And then from that, we build a hierarchy. So we just define corresponding densities in the same way that we did up here. So just a product over x1 through xk and x1 prime through xk prime with bars. And then we can show that this new hierarchy solves a hierarchy of its own, and it's given by this form, where the bnk plus 1, the collapsing operator, is the same as the one in BBGKY, and then the only difference between this and BBGKY is that there's no potential term. There's no 1 over n of Vn upper k times gamma upper k in there. And then this coefficient is 1 rather than being n minus k over n. All right, so that we'll call the Hartree hierarchy, just for convenience of reference. So we'll call the difference then between the NLS hierarchy And the Hartree hierarchy, we'll call that rho upper K. All right, so that is, you take this hierarchy built from NLS solutions, and then you take this hierarchy built from Hartree solutions, and then take the difference. And then effectively, since each is just built out of products, you have something like a difference of powers going on here. So you should think of the difference as being effectively, you'd have the Hartree minus the NLS in some component J, and then you're otherwise multiplying by the rest of the phi's or the phi h's. Right? So there's an expansion that looks like this, and then similarly for the primed components. So this is the first order component of the difference, and that's really the way to think of what this looks like. So then, on the other hand, let us take BBGKY hierarchy and the Hartree hierarchy and take the difference and call that omega K. All right, so the BBGKY is the one built from the n-body linear Schrodinger evolution, and then we take the difference with the Hartree, and then we want an equation that solves. So we take the equation for BBGKY here, so it includes the potential part term, and then we take the Hartree hierarchy that I had written down before, and that is solved by gamma h upper K, and then when we take the difference of the two, we get on the left-hand side, we'll get gamma nk subtracting gamma hk, so that is omega, and so it's I dt omega k. Likewise, Laplacian terms subtract and leave us with this contribution. And over here, when it comes to collapsing operators, the n over n matches perfectly up with the term here. And so that's going to leave us with bnk plus 1 omega k plus 1. But it wasn't an exact match, so there's still the negative k over n bnk plus 1 acting on gamma n k plus 1. Right, and then the potential term for the BBGKY had no corresponding term in the Hartree hierarchy, so that just has to be copied down. But now you can look at this. So this is now a hierarchy in omega k for this difference, and we see that on the first line, it has no potential term, and it's just the same as the Hartree hierarchy. But then there are forcing terms driving it on the second line, and those forcing terms are all prefaced by a 1 over n. All right, so then there's some hope that you can, if you have sufficiently good estimates, that you can capture gain of from the 1 over n gives you a gain, and so this forcing is relatively small. So the difference that we're interested in is the BBGKY hierarchy minus the NLS hierarchy. So that was gamma nk minus gamma k. So our technique is to pass through the Hartree hierarchy. So we look at gamma nk minus gamma hk plus gamma hk minus gamma k. So that is, we look at omega k plus rho k. And then we separately estimate omega k and rho k. So the analysis of rho k reverts to studying the difference between one particle but nonlinear Schrodinger and Hartree solutions because of that effective expansion that I showed you on the previous slide for rho k. All right, so that is effectively a nonlinear comparison. But the estimate on the size of omega k is a true hierarchy analysis. We have to apply estimates to this equation for the hierarchy. So the features of our analysis are the following. So it is the first result with a quantitative rate in the BBGKY to GP framework. So there are previous results in which the convergence is proved with this framework, but not with an explicit rate. All right, so on the other hand, rate estimates are available, previously available, via another approach to the whole problem, which is through the Fock space. And so these approaches were introduced by Grylakis and Machedon, and also Benedicter, Oliveira, and Schlein. And then there has subsequently been many other papers by Lewin and Nahm, and Heinzel and Pickel and Bosman, as well as additional papers by these authors, and they've pushed the method quite far. But it's a completely different framework for studying multi-particle systems. The Fock space is some kind of tensor algebra representation in which of increasing order, and Bose-Einstein condensate refers to Poisson distribution in those tensored components. And then the Hamiltonian has to be represented as acting on that structure in terms of annihilation and creation operators. And then the evolution is studied and estimated by a procedure called the Bogoliubov transform. But it's a different framework, and it is the basis of studying quantum field theory. So it's just a different way of looking at the whole thing. So we wanted to do it directly from n-body and its equivalent formulation in terms of BBGKY. So our result, another feature, is that it's improved entirely at the regularity of H1. So it's all energy space. The initial data is in H1. The energy bounds that we assume on the n-body Schrodinger are H1 type, and the convergence rate is proved in H1. So the alternative approaches via the Fock space approach prove the rate estimate in the trace norm. So that is something that has zero derivatives. But then they assume that the solution is controlled in HS for some large S. So we don't have any gap in regularity between the bounds and then the space in which the rate is proved. So H1, getting things in the energy space, it might be just a mathematical obsession, but it is also, it's the level of the kinetic energy, and so thus it's physically natural. And so in fact, if you it's possible, it's hard for us to read these physics papers, but my collaborator is looking at them intently, and he's thinking that the external potential that they have in the experiments is not really that smooth. And so as a result, it's nice to not add additional derivatives to the analysis, because that would hit something that is not so smooth and affect your bounds. But so our result has nearly the optimal rate. All right. So n to the minus beta is the optimal rate, and we have a log n over n to the beta. And that is because of the estimate of rho k. It's actually in the nonlinear problem. We use some bilinear estimates, and we just left with Littlewood Paley decompositions, and had to sum over all the dyads, and then it's in that summing process that we just couldn't do it without a log loss. So, but we can erase that log loss if we accept, if we do H1 plus epsilon in H1, we can get rid of it. But the whole point was to try to do everything in H1. So the Fock space approach has very recently achieved the optimal rate. So in the last few years, they've gotten the optimal rate, but they still have the regularity gap. So our result also directly proves the strong limit without passing through weak star limits and then upgrading the weak star limits to strong limits via minimality and convexity. All right, so the weak star approach was employed in the first papers on the subject. Erdős, Schlein, and Yao in 2005 to 2010 wrote a series of papers, the groundbreaking work, doing this BBGKY to GP convergence, first complete proofs, but without estimates on the rate. And the convergence they proved with compactness and compactness arguments and weak star limiting procedure. And so since we just have a way of writing down the difference and estimating that directly, we get a strong limit directly. We also avoid the compactness step in just writing it that way. So what we don't have to do, one thing that they had to do, it was prove that the solution to the limiting object, so that is the solution to the Gross-Pityevsky equation, is unique. And then that gave them uniqueness of the limits, so that there is a single limit in the convergence of the sequence. So we don't need results on uniqueness of GP solutions when we do it this way. We also do not use the quantum definity theorem, which has been introduced, very effectively introduced to the subject by Thomas Chen, Pavlovich, Heinzel, and Seringer in 2003. But it does involve some additional constraints. In particular, you can't really use it directly on R3. You have to work in a, well, I mean, that's, maybe that's not so accurate to say that, but it does have some limitations, especially when you try to use it for BBGKY representation. Let me say that the components of the proof. All right, so it's looking at my time here. So I just got maybe 5 minutes or so.
Yeah, sure.
Yeah. Okay. All right. So the components of the proof are, first of all, passage through the, as we said, passage through the Hartree hierarchy en route to the NLS. And then representing this difference in terms of the two pieces and then estimating each piece separately. So the omega k hierarchy we take and represent it in Duhamel form, as an integral equation. And then that is iterated multiple times out to coupling level log n. And at that point, once we've made it that far, there is a balance between the forcing part and the interaction part in the equations. And this is an idea that we borrowed from Thomas Chen and Natasha Pavlovich in 2013. They have this paper, and then we applied it in a paper in 2015. But we're using that again here. And then we need to use the Klainerman-Machedon board game to reduce the number of Duhamel terms. And the reduced Duhamel terms are estimated via the estimate that they give, which is called the Klainerman-Machedon trilinear estimate in the subject. We also use some dual Strickert's estimates. Study of the rho k hierarchy, which corresponds to the difference between NLS and Hartree evolutions, is reduced to a one-particle nonlinear equation comparison, for which we prove a biscattering theorem, giving a global and time comparison. So if you're familiar with dispersive literature, which, if that happens to be your background, so you know all about Strickert's estimates and Byler-Strickert's estimates, then our paper ends up being self-contained, not appealing to many of the many-body results, except for we do appeal to the many-body energy estimates as were proved in Erdős, Schlein, and Yau, but otherwise do not use their methods. And then we make full use of the content of the paper by Klainerman-Machedon in 2007, which introduced their board game argument and their trilinear estimate. But that is a 13-page paper. So so then we've reduced the prerequisite necessary to make it through the argument. So this biscattering theorem that I mentioned, that it makes the comparison between Hartree and NLS solutions. It's the nonlinear comparison theorem. That makes use of results on scattering for 3D NLS and 3D Hartree. So I have a paper on that together with Tomas Doikar and Svetlana Rudenko, but there's also previous results. In fact, since it's a defocusing problem, the appropriate citations for this are, it was done by Ginny Bernvelo in 1985, and that was done using Morowitz estimates of Lin and Strauss from 1978. And there's also a Morowitz proof based on a Morowitz type approach by Colliander, Keel, Stoffalani, Takayuki, and Tao. And then Hartree adaptations of all that were given by Miao, Xu, and Zhao. And what we also use in that analysis, the U and V spaces of Koch and Totaro. So I think, right, okay, one more slide would be a good place to wrap things up. So a weakness in our result relative to the Fox-based approach is that we're currently limited to beta less than 2/5. And you really like to push it all the way to beta equals 1. So we have, but we have not yet applied all the other methods that we know. We wanted to to do this with as quickly, make it as short as possible, get a complete result that's as short as possible. So we have not yet applied the wave operator methods that we developed in 2016 for this. And with that, we think we can get at least closer to beta equals 1. We're currently limited to a short time, and this I found rather frustrating that couldn't go beyond E0 to the -2. And that comes from the hierarchy analysis, not from the nonlinear analysis. Nonlinear analysis is global in time. But the Fox space work does obtain a longer time. It allows you to reach it allows you to prove a bound which is global in time, but has a coefficient e to the t. And so that means that it gives you something with content all the way up to time log n, right? So at least mathematically, that is a growing time interval in the limit as n tends to infinity. But of course, if n is 1,000 or 2, then log n is 1, right? I mean, it's not really a long time because it grows so slowly. But at least they achieved what we could call a long time result. Truly, we would like to really tap into scattering, which we can do for nonlinear problems, but not so easily in hierarchy analysis, and get something that's more global in time, genuinely more global in time. All right, so I think, of course, I just kept writing, but I knew that I'd have to stop at some point. So I'm going to stop here and ask you if you have any questions. And
okay, so thank you for the nice talk.
Okay, thanks.
Any questions for Justin?
Oh yeah.